continue the talk of Nick. I initially felt a bit inadequate in this task because I didn't realize how gigantic a task it was until I started surfing literature. And I'm sure that in the audience there will, for everything I say, there will be somebody who knows a lot more than me about that. So I apologize in advance to essentially all of you. But I would like to briefly discuss pair formation models, metapopulation models, spatially explicit models, households, networks, and conclude with some comments. So, oops. Okay, so pair formation models have been introduced to better model sexually transmitted disease transmission in partnerships, and work on pairs date back to work in demography by Kendall. But for sexually transmitted diseases, a lot of work has been done by Dietz, Hadler, co-authors, and Miriam Kretschmer, and more recently taken further by Martina Morris and co-authors. The basic idea is that we have susceptible individuals and infected individuals, but also pairs. And pairs form and dissolve at certain rates. And on top of this pair dynamics, we add the transmission. And transmission can only occur in a susceptible infected pair. So we have equations like these ones: susceptible, infected, SS pair, SI pair, II pair. And we have to decide how single individuals meet to form pairs. But if we want to compare this with homogeneous mixing models, we know that if the pair dynamics go extremely fast compared to the disease dynamics, we recover back the homogeneous mixing case. And but in general, the presence of pairs reduces the spread and are not thanks to sequential infection. So pairs of susceptibles are protected, and pairs of infectives waste the infectivity on each other. Comparing models with pairs and without pairs is not always easy, but if the comparison is made at constant R0, Kretschmer and Dietz show that the speed of spread is reduced, but the endemic equilibrium is always higher. And to the same R0, we can have two different real-time growth rates associated to it, and two endemic equilibria. So knowing only R0 is not enough for predictions. One needs to know also about the partnership dynamics. And a practical conclusions is that if partnerships are not too short, then acute HIV phase might be less relevant, and asymptomatic stage might be more relevant than expected. The model has been extended in many different ways without adding concurrency and trying to add concurrency, but the model is not really suitable to add concurrency. So one needs to move to full network models, pairwise approximation, or stochastic simulations. There have been quite a lot of work on concurrency, which is very interesting, but it's a tiny bit off topic, so I have to skip that, unfortunately. Metapopulation models, they're born in ecology. The first formalization with patches that can be occupied or unoccupied is due to Levin's. And as it has been extended in many ways, and a lot of work has been done, especially in the ecological literature by Ilka Hansky. And but the idea is that in many cases, one's aim is to study extinction, so the models are most of the time stochastic, but can be formulated in a deterministic sense. This is an example. This is basically a multi-type model. There is no difference, conceptual difference, except for a spatial interpretation. The type of an individual is usually the location where the individual is. And these models are usually SAS or SIR types with demography, because one studies oscillations, extinction, and synchrony or asynchrony of epidemics. In the simplest case of two populations, one can reformulate the model by making a coupling parameter sigma explicit in the equations that tells how much infectives in one location transmit to susceptibles in the other location. And Killing and Rouhani show that if one can recover that model by starting with a more mechanistic approach where individuals move from one location to the other, and if one makes these movements extremely fast compared to the disease dynamics, then we can invoke a timescale separation argument, and one leads these movements to equilibrium straight away, and one recovers the coupling parameter of the equations I showed before as a simple function of the fraction of the time that individuals spend away from home. Important insights of these metapopulation models are the fact that if there is no couple, we have independent subpopulations. If there's strong couple, there is synchrony. So the interesting behavior is when there is weak coupling. Other important concepts are critical community size. So in small populations, stochastic extinction is very likely, and it's unlikely in large populations. And the kind of size where there is a transition phase from one to the other is the critical community size. We see loads of rescue effects. Large population keep feeding infection in the small populations. And it has been shown that asynchrony can increase overall persistence when if population A has the infection and keeps and transmits it to population B, where the infection has gone extinct, before it goes extinct in population A, then these subpopulations keep feeding each other and lead to survival of infection everywhere. So important applications of these move from deterministic more to stochastic models, but there has been a lot of work done on measles, especially by Brian Grenfell and co-authors, and also applications of these meta-population models to pandemic influenza spread by Ira Langini, Beth Halloran, and Victoria Kolitsa. And one important result for measles is that stochastic models tend to get the critical community size, simple stochastic models tend to get the critical community size quite wrong, and meta-population models seem to be key to explain the pattern of measles in the post-vaccination era, where the prevalence has been brought down to reasonably low level, but extinction is not seen as often as it should, according to the models. Spatially explicit model, I will probably skip this one because most of the deterministic work has been done quite a while ago, so not necessarily in the past 20 years, and more stochastic work has now been done in terms of kernel-based models and gravity models, but most of the time is stochastic as far as I can say. Please contradict me if you and feel free to step in if you feel underrepresented in this talk. And I'll move straight to household models. So household models have been studied quite a lot in the past 20 years, in particular from the highly infectious disease simple case by Becker and Dietz, and the milestone paper by Paul Mollison and Scagliatomba is very important, where they defined the household reproduction number. They found ways of calculating the final size and studied the equalizing strategy as the optimal vaccination strategy that aims at leaving the same number of susceptibles in every household. And quite a lot of work after that. But for a quick overview, households are really important because there is a lot of interaction in them. The concept of household is reasonably well defined. There is data availability on households. Homogeneous mixing is reasonably justified. They are a natural target for intervention, and they are a nice laboratory for detailed parameter estimation. In household models, the idea is that there is homogeneous mixing in each household superimposed to a background homogeneous mixing in the population at large. So we have local transmission and global transmission. And some considerations about these models. They have been mostly SIR models with a few notable exceptions. In many cases in the theoretical community, density dependent has always been assumed in households, even when households have different sizes. But data analyzed by Simon Cauchemet strongly rejects the density dependent assumption in favor of a frequency dependent assumption or something a lot more complex than that. Most of the models have been stochastic because there are small groups involved, of course. An exception is the use of a Markovian model and use the master equation to keep track of households with every possible number of susceptible, infected, and recovered individuals. But even if we don't assume a Markovian model, many of the results were kind of deterministic results in a stochastic framework. So reproduction numbers, real-time growth rate, they all involve the initial exponentially growing phase, and they are kind of a deterministic limit of the average behavior of a stochastic model. So I would consider them kind of deterministic results in that sense. The early phase is by far the simplest one to study, because if we assume homogeneous global mixing and a large population and lack of prior immunity, then the household is infected only once, and it can be treated as a super individual. So I'll quickly run through reproduction numbers. And so it's difficult to define a basic reproduction number for a model with households because the small number of households does not allow to linearize the spread within the household. In particular, the first individual has many susceptibles to infect. The last one has very few susceptibles to infect. So it's not easy to decide what a typical individual is and how to average the contribution correctly. But the initial idea was to sort out the nonlinear bit within the household at the beginning, and then, assuming there are many households, linearize the spread at the level of households. And this led to the household reproduction number, R star, that is constructed in this way. We have a within-household epidemic started by a single initial case. We define mu L as the average number of cases infected in that epidemic. So in this picture, 3 gray individuals. Mu G is the average number of global infections an individual make. So the average number of blue arrows coming out of here. 2 in this picture. And then we linearize the epidemic process at the level of household by counting how many individuals are infectious in the household, 4, and each of them infects mu G, new cases outside. So mu G times 1 plus mu L is the total number of blue arrows, and if there are many households and they are all susceptible and these contacts are made at random, then the probability that the 2 contacts hit the same household is very low. So all these blue arrows infect different and previously uninfected households. So this turns out to be the average number of households infected by a single household. If we want to work a little bit more on the individual level, then we can distinguish individuals in primary cases, the first case, and secondary case for me is everybody else who is infected in the household. Even if they are a result of a chain of transmission, I pretend that they all come from the same primary case. So both primary and secondary cases infect mu G, new cases, primary cases outside. A primary case infects mu L secondary cases. A secondary case infects no other secondary case because I pretended that they all come from the first guy. And so I have a 2 by 2 next generation matrix, and Ri is the dominant eigenvalue of this matrix. Taking this idea further, recent work has led to a definition of the basic reproduction number for this model that is constructed in this way. We consider a within-household epidemic with a single initial case. The type of an infected now is the generation the infected belongs to, because individuals in different generations have a different potential to transmit the infection further. Mu 0 is the primary cases, the only individual in generation 0, and then mu 1, mu 2, and so on are the expected number of cases in each generation, which are worked out using a stochastic model. Mu G is the average number of global infections like before. And so the next generation matrix is constructed in this way. Individuals in every generation infect mu G, new primary cases outside. The primary case infects mu 1 cases in generation 1. All mu 1 cases in generation 1 are responsible for mu 2 cases in generation 2. So we can think that on average, each of them is responsible for mu 2 divided by mu 1 infections in generation 2, and so on. So we obtain a next generation matrix, and our knot is defined as a dominant eigenvalue of this matrix. This is I call it a naive construction. It's an intuitive way of approaching it, because here I have a ratio of averages and it's not really clear what I should do exactly. But if one wants to do things properly, it has to follow a slightly different route that leads to the same result.
Are all households of the same size here?
In this case, yes, but if you have a household size distribution, you just have to average over the size bias distribution. Another potentially interesting reproduction number is the vaccine-associated one. So recall that without households, we have the critical vaccination coverage is given by this formula. Now we want to mimic this in the case of households. So assume the household reproduction number is greater than 1, so we can have a large epidemic. Assume a perfect vaccine and define PC as the critical vaccination coverage in the sense of the fraction of the population that needs to be vaccinated at random to reduce R star below 1. And then define RV in terms of this critical vaccination coverage so that the same formula applies. If there are no households, RV equals R naught. But if there are households, RV is different from R naught, and it's analytically intractable. So some conclusions of this type of work is that all these reproduction numbers, and many more than one I described here, can be compared. They all share the same threshold. In a growing epidemic, they can be nicely ordered in a set of inequalities. In a declining epidemic, the order is reversed. RV is not defined in a declining epidemic. But in a growing epidemic, we notice that RV is greater than R naught. So vaccinating a fraction of 1 minus 1 over R naught of individuals at random in the population is not enough to stop the spread. However, RV can be bracketed between two analytically tractable approximations. So we can gain some interesting conclusions from there. This model has been extended in many different ways to overlapping groups, households and workplaces, household networks, and so on. If we want to work on time-dependent quantities, then we can we can consider the real-time growth rate, which is again a kind of sort of deterministic result. The idea is to linearize at the level of households, so we can use the Lotka-Euler equation that is commonly used to find the real-time growth rate. But now this beta h of tau is the average infectivity profile of a household. This can be calculated exactly in a Markovian model using continuous time Markov chains. In a non-Markovian model, only approximate results exist. And if we want to follow the full dynamics with a deterministic model, then that's the only thing I could think of. It's just using the master equation in a Markovian model to follow the number of households with X susceptibles, I infectives, and Z recovered individuals in them. And networks. The history of network goes back to graph theory. There are many different types of networks. But I'll focus on key epidemiological quantities at the beginning. In order to understand the difference between homogeneously mixing models and networks, then we can consider the definition of R naught for an SIR epidemic on a network in the simplest case of a large, static, unclustered, unweighted, regular network where every individual has n neighbors. So the first distinction is that the R naught on the network is bounded because you can't infect more than your neighbors. And then each link can see repeated contacts pass through it, in the sense that if we have a Markovian model where there is a per link transmission rate lambda and recovery rate gamma, then the probability of transmission p across a single link, instead of having this form as one would naively think, has this form here because one has to consider the probability that a transmission across the link occurs before a recovery. And that's what comes out using competing hazards. The third difference is that the first infective is special because all other infectives, if I move to the second generation here, all other infectives have one link that has been used already to get infected. So formally, R naught should be defined not as related to the behavior of the first individual, but to a secondary case onwards. The concept of R naught can be extended quite a lot when the models are a bit more complex. As soon as we introduce some degree distribution, then we have to bear in mind that the degree distribution of a randomly selected node is different from the degree distribution of a node that is reached from a randomly selected edge. Because a node of degree d is d times more likely to be reached than a node of degree 1, and it's d times more susceptible and d minus 1 times more infectious, minus 1 because one link has been used already. So if we consider the mean of the degree distribution and the standard and the variance, then R naught depends on both of them, as it does in the case of multi-type models for sexually transmitted diseases, where individuals have different levels of sexual activity. Then we have a similar formula. This time we have the -1 because one edge has been used for the infection. A better way of obtaining this result is through the next generation matrix, which can be used for more complex models with degree correlation, weighted networks, bipartite networks, and so on. In terms of dynamic networks, the slow dynamics is basically a static network where R naught is given by this formula. In the Markovian example, this P is the one I was talking about before. As soon as we make the network dynamic, when the dynamics are extremely fast, then repeated contacts across the same edge do not occur any longer. So instead of having this coefficient, we have this one, and the -1 disappears because you're not linked to your infector any longer. And so for any dynamic network with these parameters, R naught will be bracketed between these two extremes. The most difficult thing to deal with networks is the problem of short loops, and because they can break down your exponential growth, and so you have problems with defining R naught and having an exponential growing phase. The smallest short loop is a triangle, so clustering is usually defined as the fraction of triplets in the network that form a closed triangle, and clustering has been added to models also in a deterministic sense, but in very special ways. For example, by specifying not only the number of links of a node, but the number of triangles that have that node as a vertex, by asymptotic expansion and transmissibility, and a very special type of clustering in the network that comes from the fact that you have households that form fully connected cliques, so they add triangles in the network. And we can use for these tools from household models. But there is a lot more than just this type of network, this type of clustering. If we want to follow the real-time growth rate, we use again the Lotka-Euler equation as before, and the infectivity profile of a node has a component that relates to the degree of the node, which is the same as the one that we saw for R0. But in terms of the time in which infections are made, they are not. If lambda of tau is the distribution, is the time in which infectious contacts are made, we have to keep track of the first infectious contact only. So we have lambda of tau multiplied by the survival probability of the node of the other end, on the other end of the edge. We want to follow. There have been attempts to follow exact dynamics in a network, which have been successful in some cases and not in others. But if we have a small population, the only thing we can do is use the master equation to track the probability that the system is in every possible state, which is a very stochastic approach. But for large populations, we can do something if we have a Markovian model and a configuration network. Three main models have been defined in the literature, and I would like to discuss them very briefly. An effective degree model by Ball and Neal, a model based on probability generating function techniques by Volz that has been simplified by Miller, and Lindquist et al. Defined another model which they still call effective degree because it's very similar to that of Ball and Neal, and some of these models have been extended quite a lot. But the effective degree model by Ball and Neal is the only one that has been proved to be exact in the sense that it represents the deterministic limit of the average behavior of a stochastic model once all the obvious stochastic bits have been taken out, like extinction and random delays at the beginning of the epidemic. Sk and Ik are the number of susceptible and infected nodes with effective degree k, and the effective degree of a node at time t is the number of links that are still available for transmission. They formulated it in a slightly different way by making the network as the epidemic progresses, but the idea is the same one. A node decreases its effective degree by 1 when one of its edges is used in any way. So when the node is infected, the edge cannot be used any longer after that. Or when the node transmits to a neighbor, again, the edge has been used. Or when a neighbor recovers, the edge that links the two also cannot be used for transmission because the other guy has recovered. So the equations are of this form. They are quite complex, but we can recognize a few terms. So if we consider an individual of effective degree k plus 1, this individual will become an individual that is infectious and with effective degree k if infects somebody else, so remains infectious but has used one edge to infect. If it was susceptible and gets infected, so it becomes infectious and one edge has been used. If it was infectious and an infectious neighbor tries to infect him, the infectious attempt does not result in an infection because the guy was infectious already, but it burns one edge. And if the neighbor, if a neighbor of an infected guy recovers, then one of these edges, the edges that connect the two, disappears as well. The model by Volz is based on probability generating function techniques, and the main variable is the probability that the random edge has not transmitted yet, or equivalent to the fraction of degree 1 nodes that is still susceptible at time t. So if psi is the probability generating function of the degree distribution, then Volz came up with a system of 3 ODEs, and Miller showed that the same system can be written equivalently into a single ODE of a single variable that can be from which everything else can be obtained. Yes?
Do you want to ask a question?
No.
Okay.
I was signaling that you have 1 minute left.
Oh, okay.
Fine. I'll quickly skim through things. And the Lindquist model is again an effective degree model, but now we're keeping track of the susceptible and infected neighbors an individual has. So an individual that gets infected or recovers changes its state, but not the indices because nothing happens to the neighbors. And if something happens to the neighbors, then the state of the individual doesn't change, but the neighbors, the indices change because something happens to the neighbors. By doing this, they could, unlike Ball and Neal, they could model an SAS transmission as well as an SIR transmission, which follow the same routes. Some important conclusions: they managed to define R0 for an SAS model, which is a network model, which is not easy at all. and they show that this is always greater than R0 from an SIR model. And but it's not yet clear if this model is exact as Bolle-Mills model is, and there are suggestions that Voll's model is not exact. And very quickly, I'll flick through approximate dynamics. If somebody knows they want to be approximate already, they can go straight to moment closure. The idea is to approximate the average behavior of a stochastic network model with a few deterministic equations. And the simplest thing to do is to consider a mean field approximation. So the number, square brackets are number of individuals or pairs or any other subgraph in the network. So the number of susceptible and infected changes when there is an infection. An infection can only occur in a SI pair. These equations are unclosed. We need to write equations for the SI pairs. That will depend on the triplets, and the triplets will depend on 4 node graphs. So the simplest closure is to assume that the number of pairs is the product of the number of singletons, and we end up with a simple deterministic SIR model. But if we want to be a bit smarter, we can write the equation for the pairs and close this system of equations at the level of triplets. For an open triplet, that's the basic closure that has been used. For a closed triplet, it's a more complex, introduced by Kirkwood, and then Keeling in 1999 popularized a linear combination of the two, where the linear combination is given through the clustering coefficient. Loads of extensions. I mentioned only the maximum entropy one, which has a strong theoretical solid ground behind it, but it's a lot more complex than all the others. And there have been results of using the use of these models. For example, we have a system of ODEs, so we have simple approximate results for R0 and little r, and the full transient dynamics. In practice, they have been used for sexually transmitted infections, foot and mouth disease, contingency planning against smallpox. A few important results: the SIR pairwise is exact, turns out to be exact for unclustered networks, and the SIR pairwise model has been shown by House and Keeling to be equivalent to Voll's model with the probability generating functions. Final comments and remarks. Deterministic models, there is quite a lot of stochastic model coming up in the past 20 years, and there will be more and more over time, but deterministic models will never disappear because most of the results are a lot simpler on deterministic models, so it's always the first thing to try, I would say. There is not a clear distinction between stochastic and deterministic any longer, I would say, and most models are formulated stochastically, but the results are the deterministic. Many models have been introduced here. We need more effort to compare them. It's not always easy to decide how to compare them, but my suggestion is to find a relevant quantity to keep fixed between them that have the same biological interpretation in both cases. And future challenges, everything that does not involve an exponentially growing phase, so the presence of small population, hierarchical societies where there is a lack of group scale separation, a lack of time scale separation, superinfection, prior immunity, and more. So we'd like to thank the organizers, MRC, EPSOC for funding, and my collaborators at Imperial, Warwick, and other places. I would have put here a picture of my holidays, but I think people in this audience have worked way too much in the past 20 years. So I didn't really have such a big holiday. And so I would like to thank you all for having worked that much, and more seriously for listening. Thank you.
Thanks very much. There's room for a few comments.
So when you say the false model is not exact, what do you exactly mean?
I know, it's a big issue. I'm not going to attempt an answer here. But if you define a stochastic model and you try to compare individual-based stochastic simulations with that model, with the deterministic model, you try to average over stochastic simulation and you try to solve your deterministic model, the two don't always match. There is a discrepancy.
There are limit theorems which say that the false model is a good approximation to stochastic.
It is a good approximation, but
I mean, large population exact in that sense.
Yes. Okay. Good. Perfect.
But you have to start with a positive fraction of the population already infected.
No, you don't. This is in our recent paper, in fact. I mean, I know Viet Tichan's paper starts with positive fraction, but you can start with one.
That's quite.
And of course, there's a random time.
Yeah,
start.
the random
Too
time.
high.
I was.
So it's, you can sort all that.
Okay, that's. I'll can I talk to you? Hello. No, I'd like to.
Together at lunch. Yeah. Peter?
Yeah, I have a question about the SIS model of where you were hinting at, with the linguist.
Yes.
I have to admit I haven't read the paper,
Yeah.
but my strong suspicion is that things might go wrong at the same level where the paper of Vespigiani and Pastor Sassores goes wrong, and that they don't consider longer range in dependencies. So, so if I get infected,
Yeah.
then my not only my neighbors.
Yeah. I agree on that. I agree on that. SAS is a problem in networks. Yes.
And those longer range interactions are really not easy to deal with.
Yeah. Yeah. I agree on that.
Okay, final comment before we move to lunch. Okay, so thank you. Lunch is going to be at Wolfson Court, that's next door.